Hello, YouTube viewers. Welcome to my show, Rocket Monday. In today's episode, we're going to discuss a very interesting topic of gravitational slingshots. So let's dive right into it. It has many names to it. Now, first, before we understand the solution, we have to understand what is the problem with our current infrastructure. Basically, our rockets are way too weak. Now, you have to understand this one core aspect. Let's say you talk about the most powerful active rocket in the service right now. It's basically Falcon 9 Heavy. Now, again, it is quite powerful. It can carry 60 ton to low Earth orbit. Now, here's the many people just stop at there. It's like, okay, 60 ton to low Earth orbit, everything is awesome. Now, that is absolutely true. It is quite a big achievement because right now there is no module international space station that is that big or that heavy. So it is quite a big feat. However, if let's say you want to send 60 ton to let's say geostationary orbit, which is way above than 1,000 kilometer, it is like around 36,000 kilometer. Then this rocket is like, no, I can only send to around 24 ton. And then if you are like, okay, let's send something to Mars, it will drop it down to like 12 to 13 ton. So that is the critical aspect. Our rocket is ludicrously weak if we have to send anything further than let's say Earth's sphere of influence. Basically, maximum we can send is moon. That's it, flat out. Like if you want to send to Mars, again our payload goes dramatically slower, like dramatically smaller, and our travel time also becomes ludicrously huge. Like you can use a small rocket to send big payload to very far distances, just the time it will take would be too huge. Basically you can go from let's say if, in case of India had a small rocket and it still had to do lunar mission. So what we did basically orbit erasing maneuver brick by brick, day by day. Here's the problem: it took 40 days to reach to moon. So you can easily imagine why it takes like around 2 years to reach to Mars. We can do it faster, just our payload size will go smaller. So that is the whole context here. Our rockets are way too big, basically weak. And then you have to understand, space is big. Now we cannot truly comprehend that kind of size simply because we do not deal with light speed. And to give you a context, light is the fastest thing there is in this universe. Now at light speed, let's say you left Earth and you're like, okay, light speed engage, it will still take you 1 second to reach moon. Now again you may think, okay, still 1 second, here's deal, nothing can travel at light speed. We cannot even travel like 1% of light speed. So then you start to realize, okay, even at light speed it takes that long, and flat out with our practical method it could take as long as like 3 days to reach to moon. So then you start to understand, like Mars takes years, and if you are talking about gas giant Jupiter, Saturn, Venus, Neptune, Pluto, those will take very long time. So things are very far apart. On top of that, we need speed because we can use a slower method. We can send a big probe using, let's say, Falcon Heavy itself that reaches Pluto, and it is like it is big payload. Side effect, right now if you try to do this, it will only take like 3 tons, but let's say you want to send 10 tons. Can you do that? Yes. It's just it will take way long time, very long time. And we need speed, not only like because our battery will run out, because even radioactive batteries also have a decay span to it, and not to mention electronics will also fail. So you have a time span, you must do it as quickly as possible. Now right now how we are managing it, basically we make our probe, whatever have you, and then we balance out how much rocket do we want. Like if you are sending Cassini, you will be like, okay, we want this much flexibility, so we'll add this kind of rocket. Now be understand, you are adding rocket on top of a rocket. Side effect, your payload is becoming smaller. Let's say your original idea was like, okay, I'm gonna have a payload, it's gonna have like 12 cameras, like hyperspectral camera, like I'm from infrared to ultraviolet to this and that, everything. Yes, once you have to put rocket on top of your basically probe itself, you have to remove few of those cameras because you are eating away at the space, basically tonnage that you are allowed. So then it becomes a balancing act. Like I can go there faster, but I will not have enough instrument, or I can go there slowly and I will have a lot of instrument. So that is the problem right now. No, so okay, we have the problem. So what is the solution? Solution is basically utilize nature itself. Nature has a lot of celestial body, basically bodies that are in heaven. Why not use that? Well, we can simply use that, and we can add speed and reduce speed. Now you might be like, okay, why the heck we want to reduce speed? Think of it this way: if you are accelerating at ludicrous speed, as in like orbital speeds or things of that nature, if you go to far enough from any planet, you can just skip by it. Like you will not photograph it. You will like done, like you just never. And again, if you are spending hundreds of millions of dollars, you cannot just sell to your investors like, yeah, I got one photo out of that. You have to slow down. Now again, you can utilize on rockets, or you can utilize gravitational assist. So that is why adding speed and removing speed is very critical. Then we talk about direction change. Now this direction change is a kind of odd topic, because you have to understand, like entire solar system is more or less on a plane. Like it is, like it has a elliptical orbital plane. Now not everything in this plane is exactly at, like, zero inclination. Some are top, or some are down, and for some reason, let's say you want to go on top, like you want to capture star systems that are below it, or star systems that are above us. For some reason, let's say you want to do that, like Voyager 1, or in certain scenarios, like in small scale, let's say you are in Jupiter or Saturn, and you want to capture its moon. Now its moon are no longer in, like, one elliptical orbit, like it has multiple orbital planes. So in those sort of scenarios, you have to have the ability to change your direction. You can rely on, giant boosters, or you can utilize the gravity itself to change your direction. That is very critical. Now all those things, if you can do it properly, if you can do the timing right, you can have something like this, like this giant probe, like, again, quote unquote giant. This probe is like a New Horizon probe, and it took 10 years to travel to Pluto. Now you may say 10 years is so long. Yes and no. Like for that distance, it's like, it's quick. It's like we went there. Like again, it took time, but it was very quick. And you have to understand, the computer did not die while traveling. That is the probe's requirement. Like you must send the probe while the computer is still active, because even though, let's say, the radioisotopic generator that we have, it will keep working, let's say, for around 20 to 25 years. Your computers will not work that for that long. So computers are the weak point at this point. And not to mention, the longer you have to stay in space, the more things will go wrong. So we also have to want to make sure, like, everything as fast as possible. So this was a very good demonstration of our mathematics, where we can time it right so well that we can, like, reach to Pluto in 10 years. Now, to give you a context how far Pluto is in human perspective, if you are standing on Pluto, you will have hard time finding sun will be like just a star. Now how does this whole thing work? Now everything in our solar system, in our whole Milky Way, is in motion. Basically we are going around, basically moon is going around us, we are going around sun is going around the Milky Way center. So everything is in motion. That's the first thing you have to understand. Now gravity, where everybody talks about, like, gravitational assist, gravitational slingshot, those are kind of misnomer, because gravity only gives you control. Like you can change the direction. Basically, if this is the elliptical and your planet is here and you want to go down, you can just aim yourself upwards, and gravity will help you guide downwards. It will not add or remove speed from you. Now that may be odd, like people are like, okay, how the heck that is happening? I'm not able to add speed or remove speed. Think of it this way, like, this is your object, and, like, this is the gravitational well, and you are traveling, okay, and you are traveling at, let's say, very slow speed, 100 kmph. Now 100 kmph, the gravity starts to catch you, and you're like, okay, 200 kmph, 300 kmph, 1000 kmph. Now here's the moment you go cross that orbital plane, you'll be like, okay, now your speed starts to go down, because gravity is in negative. It's working against you. You are basically, quote unquote, escaping the gravity. So now you have to remove the speed that you gained. So basically the total net change on your speed would be zero. Again, you will have acceleration, you will have deceleration, but total overall you will still be exactly the same speed as you enter. However, you can steal energy from the orbit, not from the gravity, but from the orbit. So everything, that is why it is very important for you to understand, everything is in motion. So let's say you have Neptune is moving. So what you will do, you are traveling, let's say, whatever your velocity is, let's say velocity a. Now gravity will not do anything. Of course, for a short while your velocity will increase because of the gravity, but that's not like the moment you start to leave it, it will go away. But because the gravity is pulling you towards the orbital axis, basically this velocity of the Neptune itself, you are gaining leaching energy away from this plane. Basically gravity will not change, but the orbital energy of the planet will. So using that, you can add your speed. Basically it's like, and gravity here is just acting as a tug. Basically it's acting like a magnet. So you're not taking the energy from the magnet itself, you are taking the energy from the person who's carrying the magnet. So this planet, in this scenario, so you will slow down the planet. How much? Again, if we did that, like hundreds of trillions of them, then you may able to slow it down to, like, around 1 year. Like it will lag 1 year where it's supposed to be in 100 million years. So you have to understand, flat out, we don't have to worry about it. Like it's a planet, it has more than enough energy for us to steal for thousands of generation. So that is what's happening. Like you are coming here, gravity is just allowing you to control. Now again, if you time it right, if your correctional thrusters are working properly, you can aim it in any direction. Like you can aim it, here, or you can aim it here. And if you want to slow down, let's say you want to study the gas giant itself, you can just, instead of adding this velocity, you can go against it, and if you do against it, you will slow down. So that is what we are doing. We are taking the energy directly from the orbit itself. We are not taking the energy from gravity, we are taking the energy from the orbit. This is accurate term would be orbital assist, but again it does not sound cool, and gravity is helping you to control it. So that's why we say gravitational assist or planet swing shot. So that's what's happening. Gravity is not adding speed, it's just giving you the control. Now probes steal orbital energy. So one of the luckiest thing we ever had is that NASA was in a good place, and one good alignment happened. That was all the gas giant was aligned in a certain way. Now again, this alignment happens every around 100 and 117 years or something like that. The alignment was such that if we are doing correctly, like if we do everything right, we can hit all the gas giants in one go, from Jupiter, Saturn, Uranus, Neptune, all of them in one go. That was the amazing part of Voyager. Side effect, they had to do it in that time. If you miss that you have to wait 100 years. So you can understand that it was very lucky that NASA had the technology. NASA was in a good situation that it did happen, and it is like one of the most mind-boggling mission that ever was, in terms of knowledge, not in terms of like human passion and all that thing, right? In terms of knowledge, it taught us so many things. Like we did not even think there could be a volcano which is spewing water. But again, it taught us that. So I would urge you, if you really want to understand space technology, the best mission ever done is like Voyager systems. Not for human reasons, for scientific reasons. So are there any limitations to this magical trick? Well, yes, timing is the key. Basically, everything relies on your perfect timing. And I mean it, you cannot misalign it, in terms of what we call window of opportunity, how far can you be in plus and minus, because we cannot be okay, in this nanometer I will be exactly, a probe does not work with that much accuracy, but you could be okay, this is the window, I have to be a plus minus 1 or 2 kilometer. It's very narrow, it's very tight, and not to mention timing wise is also very time. You have to be let's say on 21st January you must be here, so you have to be here. If you miss it, done, there is no second attempt here. Now you have to follow the timelines of the celestial body that you want to extract energy from. That is the inherent limitation. So if you are familiar with the fact that we have to go to Mars every 2 years, that is the reason. It's the celestial body does not follow our timeline, we have to follow their timeline. Now it is very slow for humans. Now again, if you are going to moon, you can utilize gravitational assist and all that, but again, and if you are doing anything from LOPG to Saturn missions and anything like that, you will rely on its gravity to get as much out as much energy as possible. However, it will not be the main source of energy, because if you did that as a main source of energy, it simply would be too slow. So if you want to, let's say, go to Titan and you want to study that for a human mission, you cannot rely on gravitational assist. It will be way too slow. So that is the inherent limitation. It's an unmanned probe, it's awesome. For manned system, no. Now what we can expect in the future. Now again, I made a video about solar sail, light sails in my Future Friday series, and if we couple light sail with gravitational assist, we can reach, let's say, these further objects as far as Pluto in 5 years. Now how the heck that's possible? Basically we have to go towards the sun and extract the orbital energy of the sun itself. Sun has more than enough energy, and once we are in the positive side, not only we will have the energy that we steal from the orbital energy, we will also have the benefit that while going it will be parallel, sunlight is coming, it will be parallel. Once we are on the positive side, we will make it 90 degree to it, so we can get the push out of it. Using that technology, we can utilize ludicrously high speeds at the escape side. Not only will have orbital speed plus the high intensity photon that will push you, so that is quite amazing. We can achieve, there are some missions that right now on the drawing table that can give us amazing things, Voyager 2.0 basically. Now that is the first reason why we could even do all those missions in one go. It allowed us to understand gas giants much more accurately and much more controllably. To give you a simpler understanding, is right now Voyager 1 is so far away that at traveling at light speed, it will take you 19 hours. At light speed it will take you 19 hours, if not more. So that is the whole point. It is so far away that it exceeded it's outside of termination shock. Basically sun is moving, so it has a shock wave around it. Now that shock wave is in multiple layers. So one of the layer is termination shock, then you have a heliopause, and then you have bow shock. Now again, when you see this sort of fancy designs, you will think, okay, this is like giant plasma, it's shock wave. It's a very low density, you cannot feel it. Our instruments are sensitive enough, they can detect it, but it's nothing, you cannot detect it. You can be here, you can literally be in bow shock, and you would something supposed to be happening here. It's that low density, like density wise it's like, you know, one atom per like 1 meter square or something like that. It's like ludicrously low density. So do not think like this diagram kind of makes it sound like there is a giant shockwave going around. Nothing like that. It's just something is there, we can detect it, we can measure it, so we rely on that. So Voyager 1 is the furthest object that we ever sent utilizing the system. Now, again, the Voyager 1 was like done with old technology. What we can do with modern technology? What if we had the same technology and added multiple things? Let's say we added light sail and then jettisoned the light sail and then utilized ion propulsion engine, relying on beta voltics or something like that. Again, we can go very far. So this was my presentation on gravitational assist. I hope you liked it, learned from it. In that case, please click the like button. If you didn't like it, I would urge you to press dislike, press it twice to show me your extra disappointment, and please leave a comment because I reply to all of them. Subscribe, press the bell icon if you're free, and as always, thanks for watching.